This conference will now be recorded.
So, very good evening, students. Today, we'll be concluding this chapter by discussing frequency modulation, that is in short FM, and phase modulation, that is in so phase modulation in short it is PM. So, we'll start with frequency modulation. So, what is frequency modulation? So, let me tell you what is modulation as a recap. Modulation is actually modifying the carrier signal in accordance with the modulating signal. Okay, you might not be understanding what I have told. Suppose I have some audio frequency of low frequency, audio signal of low frequency. If we want to transmit it from one place to another without any distortion, then we have to modulate this audio signal, low frequency audio signal, so that the receiver receives without any distortion. That can be done by modulating it. Modulating means you have a carrier wave or carrier signal which has larger frequency than the original audio signal, and the frequency of the carrier wave will be modified according to the instantaneous value of the original audio signal. So that is actually frequency modulation. So here it is stated, it is the process of changing the frequency of carrier wave in accordance with the instantaneous value of modulating voltage. Modulating voltage means the original signal. Okay, let me show you this figure. So this is the message or original signal. We can write original or audio signal which has to be transmitted. So you can see that it has low frequency compared to the carrier signal. You look, this is the carrier signal it has. So how do you understand what is the frequency, whether it is greater or this is greater, this wave has greater frequency than this wave or vice versa. So to know whether this one has greater frequency than this, you have to check the number of oscillations, complete oscillations. So suppose this is the time axis. So within this, you look within this time, or this is the time period for this signal, obviously. So it has a complete oscillation. When you have your carrier wave within the same time period, it has actually many oscillations. You can see that. So that's why carrier signal has always greater frequency. Now this carrier signal will be modified according to this message or original signal. You can look here. Look when, how is it modified? You can see somewhere frequency is more. This is actually a larger frequency or greater frequency. You can see that. And this place you have lesser frequency. Okay, lesser. Again you have here more frequency. This place you have less frequency. So how is it modified? it is modified according to the amplitude of this message signal. You look here, when the amplitude is more or maximum, there you will have maximum frequency. Okay. So the frequency of modulated carrier, so this is actually modulated carrier wave. That means modified carrier wave. The frequency of modulated carrier wave increases as the modulating amplitude, this is increasing. When this is increasing, you look up to here, you will have more frequency. Look up to here, more frequency. And now the amplitude is decreasing from here. Look here, it is, at least it is going negative side. So you look here, it is less frequency. Similarly, when the frequency is again increasing during this time, you have more frequency again. And when the amplitude is decreasing, again you have less frequency. Okay. So this is how the carrier wave will be modified in frequency modulation. The amount by which the frequency of the carrier wave changes or shifts. Look here, actually, this is the original frequency, right? But this original frequency is not remaining here. According to this variation of this amplitude, this modulated wave has more or less frequency than the carrier wave. The carrier wave has frequency, suppose fc, and the modulated wave has frequency suppose 1. So frequency more and less, both you have. In the modulated carrier signal, you have frequencies both less and more. Okay. When the amplitude, look, this is the more, this is, suppose this is f2, and this side, this is actually f1 and carrier. So you know here what happens, you have in the modulated let me first tell you the features of the frequency of modulated wave. What are the features? Before I go for the features, let me tell you few terms over here. Okay, let me write the features itself. So features of the modulated carrier wave, in FM, frequency modulation. Okay, first of all, it will have the original frequency of the carrier wave, that is called resting frequency or center frequency. You will have center frequency. Okay, you have center frequency or original frequency of the carrier wave. Carrier wave, and along with that you will have the shifts in frequencies. You have shift in frequencies, and shift can happen both. Suppose this is the original frequency, it can have left hand side and right hand side. These are called sideband frequencies. Okay, sideband frequencies. So this side, suppose these are lower frequencies, and this side will be higher frequencies than the carrier frequency. Okay, actually the signal is within this side bands. These are called lower frequencies, or higher frequencies, these are called side bands. We'll discuss the spectrum of this frequency modulated wave. That time you will understand again nicely. But now you have to understand that in the modulated frequency, the carrier frequency will be there, and along with that there will be frequencies which are upper bands and lower bands both. That means some frequencies, as I said, some frequencies will be there which are lower than the carrier frequency, and some frequencies will be there which are higher than the carrier frequency. Okay, so when the modulating amplitude has maximum positive value, the modulated carrier wave will be having high, the maximum frequency. When the modulating amplitude has maximum negative value, then it will have the minimum frequency. And when the modulating amplitude is 0, see, you have modulating amplitude 0 at these places you have the carrier frequency itself. You have the frequency which is exactly equal to the carrier, maybe this one. Okay, there is a little bit shift in that. So maybe you can see this will have the carrier frequency here. These places, I don't know, there may be mismatch in the curve, but anyway, you have to understand that when the amplitude of the massive signal or the original signal is 0, those places you have the carrier frequency fc, and when the amplitude maximum, you have the maximum frequency of the of the modulated wave, and when it is minimum, you will have the minimum. Here I should write f max, maximum frequency. Here you will have f minimum. Okay, minimum frequency of the modulated carrier wave. Now there is a term called frequency deviation. What is frequency deviation? We'll learn that what is frequency deviation. So now we are going to discuss the second point in these features. Second feature is frequency deviation related. Let me write what is frequency deviation. Frequency deviation. Okay. So the maximum amount of frequency, like maximum amount by which the frequency of modulated wave changes or shifts, maximum amount by which the modular the frequency of modulated wave, the frequency of modulated wave changes or shifts shifts. Shifting can happen both below or above. Below or above the carrier frequency. Okay, I'll I'll write over here. So it is denoted by, so frequency deviation is actually the difference or the shift, you can say the shift of the frequency of modulated carrier wave. So we can write delta. So the frequency deviation is denoted by delta. Frequency deviation is denoted by delta, which can be written as f max. Maximum means when you have the maximum amplitude of the original signal minus fc, or you can write delta is equal to fc, that is the carrier frequency minus f minimum. So this is actually called delta. Delta have then both side. Okay, both side you have delta have, like if I draw a spectrum kind of that, so you'll have values like this, like this you have. Okay, both side you have values. Okay, we'll see in the spectrum frequency modulated spectrum, we'll see. Now modulated wave, the deviation of the modulated wave is proportional to the amplitude. That is obvious, right? Because this f maximum or f minimum depends on the amplitude of the signal. So deviation is directly proportional to the instantaneous value of, like each point there is instantaneous value. So here it is maximum, here it is minimum, here it is 0. So it depends on the instantaneous value. If you remember, we had written a sine omega t, a m sine omega t, kind of that we have written. So this is modulating wave. So depending on this modulating signal, the instantaneous value of the modulating signal, this delta value will change, because the frequency of the modulated carrier wave depends on the amplitude of the original or measured signal. Okay, so that is one point. Thus louder, see, when you have louder audio signal, that means the amplitude is more, right? So in that case you will get greater change in the frequency in the modulated carrier wave. If you have less louder audio frequency or very feeble audio frequency signal, so in that case the modulated carrier wave will have minimum change in the frequency. And the last point is that the rate of change of the deviation in frequency is actually the frequency of the original signal. I'll write over here. Third point in the picture, the rate of frequency deviation is equal to the modulating frequency. I hope you have understood this statement. I'll explain what it is. See, the rate of frequency deviation, that means how delta changes. It changes because it is proportional to mt, instantaneous value. Then the rate of change of this will be exactly the rate of change of the instantaneous value. Rate of change of instantaneous value. That means what? That means the frequency of the original message signal. Okay. I hope you agree with me. So rate of change of delta, that is the deviation in the frequency of modulated carrier wave. If delta changes in proportion to the instantaneous value of the signal, this, let us say this is mt. So it has various instantaneous values, and according to that this changes. That means what? It is the frequency of the original or the message signal. Okay, that is what it is stated. So we have learned that the amplitude of the modulated signal remains the same. Okay, one more point is that, see, the carrier wave is modified according to the change in the instantaneous value of this message signal. But in this case, you have to remember the carrier wave retains its amplitude. Retains its amplitude if this is A plus A and this is minus A. Okay, from here, then it is the original amplitude actually. This is A, this is minus A, this is plus A. So carrier wave retains its amplitude. Only changes happen in the frequency. Okay, in this case. So that is what is another point. Maybe the fourth point you can say. The modulated carrier wave, modulated carrier wave retains its amplitude. Okay, its amplitude. So amplitude remains the same, but frequency changes. And in the frequency also, we'll have three types of frequency: upper bands, lower bands, and the original frequency. That we'll see in the next. So this is the typical spectrum of FM. FM in the sense frequency modulation. This, see, in the frequency modulated carrier signal or carrier wave will retain its original frequency. As you see, this is the original frequency fc, and along with that it consists of infinite number of side bands of frequencies. See, frequencies fc plus or minus fm. Okay, infinite number of this side bands. What is this fm? Fm is the frequency of the modulating signal. So you have side bands fc plus or minus fm, fc plus or minus 2 fm, plus or minus 3 fm, and each, see, each of them, if you look here, this is the fc, and this band, like these two are fc and fc plus fm, they are actually separated, or their separation will be fm. Again, if you look this side, they are actually equidistant. So this line Fc plus Fm, Fc minus Fm, they are symmetrically situated on either side of this Fc, and both these two are separated by Fm. This frequency and this frequency is separated by Fm. Fm is the frequency of the modulating signal. Okay, and look, I have between these two you have again difference of Fm. Between these two you will have difference of Fm. Between these two again you will have. Similarly, in this way also you will get infinite number of side bands. Infinite number of side bands. These are called upper bands, as you see, and here these are called lower bands. And amplitude, in this case, you look, amplitude actually gets modified. Only the carrier amplitude is more, and then generally amplitude of the higher side bands will be reducing as you go for higher and higher side bands. Okay, so look, this is the maximum. These are the maximum side bands, and then it will go up to minimum. Okay, so the number of side bands with significant amplitude depends upon the modulation index, that is called. So I'll just write few points on this spectrum. Before that, let me write one term and discuss about it, that is the modulation index. We had learned in case of amplitude modulation index. Here also we will define modulation index. Modulation index, this is generally denoted by mu f or mf, modulation index of frequency modulation. Okay, that's why it is f. So this is defined as the ratio of the deviation in the frequency to the modulating frequency. This is the definition. The modulation index mu f for an FM wave, that means for a frequency modulated wave, is defined as the ratio of the maximum frequency deviation. Okay, so this is called maximum frequency deviation, delta max, maximum frequency deviation to the modulating frequency. Okay, maximum frequency deviation to the modulating frequency. Now with this definition we'll try to understand few points about it. The number of side bands. Now it is stated the number of side bands with significant amplitude. Like say in this case, this is with significant, at least up to here we can say with they have significant. Obviously this we can just neglect. We can go up to here. They all of them have the significant frequencies. Sorry, amplitude. So how many side bands will be there with significant amplitude? That depends on the frequency deviation. See, or sorry, that depends on the frequency deviation index. If the deviation is maximum or deviation increases, then mu f increases, then the number of the side bands with significant amplitude will increase. If suppose the modulating frequency is increased by keeping this deviation in the frequency same, then in that case the number of side bands with significant amplitude will be less. Okay, the sidebands are actually separated. If you see from the carrier, sidebands are separated from here. It is FM. If you look up to here, it is separated from carrier by 2 FM. Then this guy is separated by 3 FM, like that. Okay, so I'll write the features over here for this. So FM wave consists of carrier wave FC, carrier frequency, and an infinite number of sidebands of frequencies FC plus or minus FM, or FC plus or minus 2 FM, or FC plus or minus 3 FM, like that it goes. Okay, it goes up to infinity. So as I said, the number of sidebands with significant amplitude depends on the modulation index. Second point is number of modulated frequencies, sorry, number of sidebands, I'm sorry, number of sidebands depends on the modulation index. If the index increases, then this number, okay, number of sidebands with significant amplitude, significant amplitude, amplitude. Okay, and the last point is the sidebands at equal distances from the carrier wave has equal amplitude. You can see that if this is FM distance away, you look another FM distance away on the other side, they have the same amplitude. These two guys will have same amplitude. These two guys which are equal distance away from the carrier frequencies, they will have the same amplitude. I think this is this guy, this will be this guy, so they have the equal amplitude, you can see that. And this, if not, maybe there is a defect in that drawing, otherwise it is like that. Okay, so FC plus FM, FC minus FM, they will have the equal amplitude. Then FC minus 2 FM, FC plus 2 FM, they will have the same amplitude, like that it goes. And what about the bandwidth here? What is the bandwidth in frequency modulation? What is the bandwidth? Actually, bandwidth is 2 into N into FM. What do you mean by 2 into n into fm? What is this n? N is the number of significant bands, right? Number of significant bands, where n is number of significant bands. Significant band. Like, see, if you have 10 number of significant bands, like up to 10, then you have fc minus fm till you will have fc 10 fm, fc minus 10 fm, or plus. So this side you will have some 10, and other side you will have another 10. Okay, another 10. So you'll have 10 fm here, and another side you will have another 10 fm, right? If you add them, then what you get is called bandwidth. So that is 2 into n, or 10 into fm. I hope you agree with me. I'll just repeat this. See, n is the number of significant bands. I'll erase this. Let me erase this. bw, let me write bandwidth. bw is equal to 2 into n into fm. Fm is the frequency of the modulating wave. This is number of significant bands, side bands, number of significant side band. Okay, so here, as I was taking the example of 10, suppose you have some 10, so you have both side, you have fc minus 10 fm, then you have the line fc minus 9 fm, like that it goes 1 to 10. So you will have, see, you'll have the difference from fc to this. You will have 10 fm, the least one. You will have the difference in this side 10 fm, and another side you will have 10 fm. So you have actually 20 fm. That's why it is 2 into n into fm. Okay, so these are the features of the spectrum of frequency modulated carrier wave. But here you have to understand that modulating wave is the actually sinusoidal wave, and in that case it is like this. So here modulating, you have to remember that modulating signal is a sinusoidal one. Okay, the sinusoidal one. Okay, so this is all about frequency modulation. But let me finish this frequency modulation by citing some advantages and disadvantages of this. So let me first write what are the advantages of FM. In this case, look, since the amplitude remains the constant in FM, so the amplitude limiters can be used to reduce the noise. So here actually noise can be handled. Okay, noise can be tackled or manipulated. The amplitude modulation, depth of the amplitude modulation cannot be increased by, see, we have seen depth of amplitude modulation AM cannot be increased beyond 100%. But in case of FM, there is no limit. Okay, there is no limit. No limit to this. Okay. In FM, standard frequency allocation provide a guard band between commercial FM station, and this reduces the adjacent channel interference. So interference becomes less. In case of very high frequency VHF, which is used generally in television, or AUHF, ultra high frequency bands, where FM operates. So in this range has very less noise. Generally FM is operated at ultra high frequency or very high frequency, so there the noise is less than AM amplitude modulation, because amplitude modulation operates in high frequency or the modulating frequency MF. So that's the reason. In case of FM transmission, high fidelity reception is achieved because of the presence of large number of sidebands. Actually, a high fidelity will be received. Okay, so achieved. A high fidelity reception will be achieved in FM because of presence of a large number of sidebands. So these are few advantages, but there are disadvantages also. Disadvantages, let me write disadvantages. Of FM. What are those? In this case, first one, channel required in FM is 10 times wider than in AM amplitude modulation. Second point is the FM receivers and transmitters both are very complicated. Are complex and costly also. In case of amplitude modulation, receivers and transmitters are very simple and less costly. And third is, in this case, FM reception is limited to line of sight. So its area of reception is much larger than that of AM. So area of reception is much larger than that of amplitude modulation case. Okay, so these are few disadvantages. Now we'll see few ranges of commercial radio and TV broadcast frequencies. So some commercial frequencies I'll tell you, frequency bands in FM. Actually we'll see FM bands, frequency modulation bands in radio and TV, radio and television. See, AM radio, it has frequency band 0.5 to 20 megahertz. FM radio, it has bands 88 to 188 megahertz. Sorry, 108. And V is very high frequency, which is used in TV, television. So it has frequency band between 47 to 230 megahertz, whereas U ultra high TV has 470 to 960 megahertz. Okay, these are few commercial frequency bands. Now we'll see about phase modulation. We'll not go into very much details in phase modulation. We'll just learn as completeness. So what is phase modulation? In this case, in this type of modulation, phase angle of high frequency carrier wave. So in this, phase angle of high frequency carrier wave changes in accordance with the instantaneous value, same thing, instantaneous value of message signal. Okay, okay, so I think I'll erase the writing part. Look here, this is the carrier high frequency carrier signal. Okay, and this is the message signal which has low frequency. Message signal, and you look the phase modulated phase modulated phase modulated carrier signal or modified carrier signal. Okay, so in this case what happens, the phase changes in accordance with the the frequency of the phase modulated wave changes. Frequency of the phase modulated wave changes in accordance with the phase angle of the modulating signal. I'll write over here. So here the frequency of phase modulated wave, that means this resultant wave, carrier wave, changes. Frequency will only changes in accordance with the phase angle of the modulating phase angle of modulating signal. I'll explain why what it is. So suppose phase angle is 0 over here. Phase angle is some 90 over here and 2 pi over here. Like if you see the phase difference between this point and this point is 90. This point is again 90. But this point and this point is actually 180 degree out of phase. They are 180 degree out of phase. Look how frequency changes. The frequency change in the frequency will be maximum, or the frequency will be maximum when the phase angle is 0. So frequency will be maximum when the phase angle is 0. Okay, so that you can see from here, this part. Okay, and I hope here in this figure there is some mismatch. Actually here it should be like this. Okay, this denser, like that should be. Okay, let me draw here. So look here it will be actually having more frequency, but here again phase angle is increasing, so there will be less frequency like this. Now here it will be much lesser frequency because here phase angle is pi. Again the phase angle is increasing this way, so you will have greater frequency over here. Again from here, like up to here, you will get greater frequency, and after that frequency again will be decreasing like this. So this figure has some issue. I'll I'll show you the correct figure in the next day. I'll stop it here for today. So you have to understand here that the frequency of the phase modulated wave will be maximum when the phase angle is 0. It decreases when the phase angle increases. Let me explain this. The phase angle is increasing. As increases, the frequency will be less. So you have more frequency over here, then frequency decreases like this. Okay. And again here frequency is 0. So you have actually up to here you will have less frequency. Again frequency will be increasing, but amplitude remains the same. Okay, so here you will have more frequency again at this place. Then again frequency decreases like that. But at this place, actually when the phase angle becomes 2 pi, then frequency becomes again maximum. Okay, I'll show you the correct figure. Okay, this has some issue. Let me not explain now with this figure. I'll come up with a modified figure in the next class, and that time we'll take a few numerical examples on this frequency, all the modulation part. Okay, so next class will be on numerical applications of this phase modulation, frequency modulation, etc. And this phase modulation I'll discuss again with correct figure. Okay, so thank you for your cooperation and patience. I'll stop it here for today. Deepa, if you have any question, you can ask me in the next class. Today it is already late, so bye for today.